about. Today, I'm going to go over stuff that you need to know for exercise 6, which is surface currents and thermohaline circulation. So here's a map of our major currents. And so you'll notice right off the bat, so we've got our red arrows, which is our warm water, and our blue arrows, which is our cold or cool water. And you'll notice a pattern, right? So on the eastern side of continents, so over here on the East Coast and over here on the East Coast of South America, we've got warmer water, right, stemming from the equator. And on our western coasts of continents, we've got colder water stemming from our polar regions. So, if you've been to California or the West Coast, or you've, heard in shows or movies how they talk about how cold the water is, it's because that water is coming straight from polar water, so it's freezing. Same deal as near Peru and Argentina, that water comes from Antarctica. Same deal for the western side of Africa. That water's coming from Antarctica as well. Up here on the western side of Europe, near Portugal and France and England, there is some warmer water, and that's because of just wind currents and ocean basin geometry in general, which we'll talk about a little bit later. But this really puts into perspective how far north London, Berlin, Wales is, and how relatively habitable it is. So for example, if we go straight east from London, we end up right in the middle of Russia and in Siberia, which is, I think, the most famous super cold place in the world, right? It's, humans, of course, live there, but it's freezing. And it's definitely not the same weather, the same climate as London, which is, pretty hot in the summers, pretty cool in the winters. Same deal for Canada. So if we go west of St. John's, we end up again in a tundra-like climate. So it's very cold. It's got permafrost, habitable for humans, definitely, but not some place where you're going to be wearing like tank tops and shorts in the summer. Or if you do, it's like for 1 or 2 days. And the reason why we have such different climates, depending on whether we're in continent or on the coast, is because of these nice currents, these warm water currents. So in fact, if these currents weren't affecting our weather patterns, it'd be freezing cold up here, and it would be a place where humans could live, definitely, but not as nice and warm as it is today. And so our currents affect our weather. That's also why in the mid-continent region, so in Minnesota, North Dakota, Kansas, Nebraska, those places, yes, it's definitely cold. That's why they have those big snowstorms, but it's also because they are extremely landlocked. So they are getting very cold weather that isn't influenced by any warm streams or currents. So they don't have really basically any warm weather influence from these streams. They have to rely basically straight up on axis tilt and stuff like that. That's why in these mid-continent regions, we get these crazy snowstorms. There are 2 types of currents. So we've got surface currents, which is above 1 kilometer or 1,000 meters, and they're driven by dominant wind directions. And we also have deep currents, which are below 1 kilometer, and they're driven by the differences in seawater density. So you'll notice, right, if we look up on the northern hemisphere and the southern hemisphere, that our currents are sort of spinning in 2 different ways, right? So in our northern hemisphere, we've got our currents spinning to the right. And in our southern hemisphere, if I was facing the south, our current would be spinning to the left. And there's a reason for that. And it's called the Coriolis effect. So there are 3 dominant gyres, which are circular passive oceanic current, and they're between latitudes 0 and 30. That's the Hadley gyre. There's the Ferrel gyre, which is between 30 and 60, and then the polar gyres. and they form because of the geometry of the ocean basin. So, basin, you already are thinking about a bowl, and the dominant wind directions. So that ocean basin is going to naturally create an area where we've got warmer water on top and colder water in the bottom. We also have the factor of salinity. So colder, more saline water is going to be more dense, and so start to sink. And we'll talk about that a little bit later, how that affects these gyres. And then, of course, our wind directions, which is affected mainly by the Coriolis effect. So like we sort of talked about, or began to talk about, the Coriolis effect causes air masses to be deflected from a direct path of travel. So if I'm standing here at the equator and I throw a paper airplane, you would expect or intend it to go straight up. But what it's actually going to do is it's going to bend to the right. And same deal for if I threw it straight to the south. If I was facing the south, you would expect it to go directly south, but instead it's going to bend to the left. This affects weather patterns. It affects ocean currents. It affects air travel, right? So if you've ever taken a flight from Charlotte to New York, or Charlotte to Chicago, or Charlotte to Miami, or South America, even over to Europe, you'll notice that your flight, if you look on the little map of your airplane, it's not going to go in a straight line, right? It's always curving. If you go to Europe, it curves up because we're in the northern hemisphere. If we were in the southern hemisphere and you were going somewhere closer to the equator, or into Southern Africa, Australia, New Zealand, it would curve down. Same sort of deal. This is all because of the Coriolis effect. Well, one, because of the Earth is curved, and two, because of the Coriolis effect. It's a really weird phenomenon, but it's caused because different parts of the Earth move at different speeds. And you might at first be like, what? That's crazy. That's not what's happening. If that was happening, then our Earth would be like, pulling apart everywhere. But if you think about it, you already knew this, right? So if I had a dot, I wanted that to be filled in. Whatever, the rest of them will be filled in. So if I have a dot on the equator, I have a dot here. Imagine that they're all in a line. I'm just not that talented. If I have a dot here, and then I have a dot way up here at the Arctic, right around the axis. So you all know that it takes 24 hours to move, for the Earth to rotate. One rotation takes 24 hours. And it takes 24 hours no matter where you are on Earth, right? It's not like if I go to LA, it's suddenly going to take me 36 hours or something like that, right? It's 24 hours no matter what. So imagine that you're standing at different places on the Earth. So we're going to start in the Arctic. So imagine that I'm standing 5 feet away from this axis here. And it's going to take me 24 hours to move in a circle around that axis, in about a circumference of 5 feet or 6 feet. And so that's incredibly slow, right? It's going to be insanely slow for me to walk a 5 feet circumference around the axis of the North Pole. I'm going to be having to go like slower than a snail. However, if I came down here to the equator, and I had to do the same thing, I had to walk around the Earth in 24 hours, I'm going to be moving insanely fast, right? The Earth is about 25,000 miles around the circumference, right? And so that means I'd be traveling like at 1,000 or so more miles per hour, just standing there, right? Because I have to go from this spot, and I've got to go all the way around back to where I started in 24 hours. And if I did that same thing, if I started in this spot and then I had to go around this axis in 24 hours versus if I had to start in this spot and go around in 24 hours on the equator, I'm going to have to move a lot faster at the equator, right? Everybody agrees on that? So even though we're all here on Earth, how far we are from the equator determines our forward speed. The farther we are from the equator, the slower we have to move, right? I'm snail's pace, slower than a snail up here. Here, I'm like, I don't know, something very fast, Superman, right? So you can imagine at these different dots, again, back to that airplane analogy, if I would throw an airplane from the equator, it's going to seem to curve, or the actual path is going to curve to the right, because things up here are moving slower than things on the equator. And same deal over here. If I'm looking south, it's going to curve to the left for the same exact reason. All right. So we can see this in weather, especially with hurricanes. So probably everybody has seen on the news a map of a hurricane moving across the Caribbean or up into the Gulf or something like that. And so when you see those storms moving on the news, if they're in the Northern Hemisphere, which that's the news we get usually, right? The weather news we get, it moves in a counterclockwise direction. So all of those hurricanes, I'm going to try to draw it. This is going to be really, really messy, so apologize. They sort of, but that wasn't, well, it is pretty horrible. Moving like this, right? They've always got this tail coming off and they spin like this. Think about the hurricane hockey logo, right? It's got this little tail coming off like this. I think it's also got another tail coming off like this, right? So it's spinning in a counterclockwise direction. In the Southern Hemisphere, it's going to spin in a clockwise direction. And I'm going to tell you why. So at the center of a hurricane, everybody knows about the eye of a hurricane, right? It's an area of super low pressure. So let's draw this out too. So it's an area, this is going to be my eye, this little yellow dot. And it's an area of really, really low pressure. And it's surrounded by an area of high pressure. So that's going to be, let's make that orange. Why not? So yellow is my low pressure. Orange is going to be my high pressure. And so just like in everything, the high pressure is going to rush to the low pressure because it needs to balance out. In nature, it can't be sustained that there's an area of high pressure with an area of low pressure without that area of high pressure trying to balance it out. You can think of it like if you set a cup of glass down, a cup of glass. If you set a glass cup down in a bowl and you poured water into that bowl, when you lift that cup up, what's going to happen? Right? That water rushes in to fill that space. And so the same thing happens here. And so as that high pressure air rushes in towards the center, because of the Coriolis effect, right? Because things move faster at the equator and slower as it moves away from the equator, it's going to be deflected off course. So just like, actually, sorry, I'm going to delete this. So just like here, things are deflected off course. Just like in air travel, things are deflected. The same thing is going to happen. So we're in the Northern Hemisphere, so it's going to be deflected to the right. And so instead of going straight towards the eye, it's going to go like this, actually. And instead of going straight towards the eye, it's going to go like this. Won't do that. It's going to do this. And so that motion, because of that deflection, is going to cause this hurricane to start spinning in a counterclockwise direction. All right. So that's why hurricanes in the northern hemisphere spin in a counterclockwise direction. If this hurricane was in the southern hemisphere, it would spin in the opposite direction. Okay, is that clear for everybody? Okay, so just one more time. At the poles, super low mileage per 24 hours. You're going really, really slow. At the equator, you have to go about 2,500 miles in 24 hours. I always get myself with the annotations. Okay, so now we know about the Coriolis effect. We can start thinking about how other factors influence currents. So I'm going to put the Coriolis effect on the back burner, and we'll talk about it in a second to bring it all together. But now I want to talk about temperature differences. So just like in plate tectonics, where we've got upwelling, right? We've got hot magma that rises up, cools down, and then sinks, right? And so that rising up, cooling down, and sinking, rising up, cooling down, and sinking causes sort of these wheels, imaginary wheels, to start turning, and it drives plate tectonics, right? So that same thing happens with temperature and with salinity. So we'll talk about temperature first, and then we'll move on to salinity. So because of density differences, basically the weight of the water that occurs due to, again, variable temperatures and salinity, we start to get these deep ocean currents. So the Coriolis effect impacts our surface currents mainly, and then density differences with temperature and saline impacts our deep ocean currents, right? Everything more than 1 kilometer deep. And so just like you all learned about isobaths, those lines connecting points of equal depth, there are also isotherms. And so those are lines connecting points of equal temperature. So iso is same, isobaths, isotherms. Iso is same or equal. Therms is temperature, right? So anything with a thermocline, for example, isotherms deals with temperature. So isotherms reflect these latitudinal changes in temperature across the ocean surface. So if you are ever like, man, I can't remember what the heck latitude is and what longitude is, I always get it confused. I gotta remember is if that is the Earth, I don't know why I did green instead of blue, that would have made more sense, but whatever, we're in it. Latitude, you can think of it as a ladder. You are climbing up the ladder in latitude. It goes north to south or south to north, either way. Oh, look at this fancy thing. This is latitude. Longitude is going along the Earth. Oh, that's definitely not what I want. Longitude is going along the Earth from east to west or west to east, like that. Okay, so one more time. Latitude, you're climbing the rungs of a ladder. You're going from south to north or north to south. Longitude, you're going along the Earth, east to west or west to east. Okay, so isotherms reflect latitudinal, so up and down, changes in temperature across the ocean surface. And these isotherms are going to highlight different layers in deep ocean currents. So, for example, a mixed layer is an average surface temperature which extends, I don't know what extern is, extends down about 300 meters depth during cool months. And so during these warmer months, the mixed layer becomes way shallower. It goes to 100 meters. And so the reason why there's that disparity between the warmer months and the cooler months is because of storms. During the cooler months, right, during, August and November, that's hurricane season. And then we've got those really crazy winter storms that create really high wave actions and so further mixing. And so if you've got higher wave action, you can mix deeper down into the ocean current, into the ocean basin, sorry. And then during warm periods, when we've got like really warm weather, calm seas, there's not as much mixing. And so our mixed layer becomes way shallower. It goes to about 100 meters. And so because of the cool month, high wave action and the warmer periods with that calm seas, a seasonal thermocline develops. And so thermo, you already know it has to deal with temperature. And then cline is a layer. So this seasonal thermocline is a layer in which a temperature changes rapidly. So again, within in cold months, we've got a pretty large mixed layer. And so temperatures can change really rapidly within that mixed layer during those cold months. And then in warmer periods, warmer months, our mixed layer is a lot more shallow. So our seasonal thermocline has a lot narrower room to change. And so you've got this seasonal thermocline, and then you also have a permanent thermocline. And so that is there regardless of seasonal variations. It's deep enough down that winter storms, hurricanes do not affect it. And it doesn't change. And so let's look at this graph right here. So we've got temperature in Celsius on top and water depth over here. And you'll notice at around 80 meters, that's where all of our lines start to diverge, right? We've got March, May, June, and August, and they all converge here around 80 and then do their separate thing. So right around 80 meters is where we have our permanent thermocline, where nothing is messing with it. It doesn't matter what month it is, that temperature of about 4.25 or 4.5 stays steady. So that's our permanent thermocline. And then above that, we start to see some variations. So in this curved layer where we've got different slopes of varying degrees, and then it shoots straight up, these slopes are going to be our seasonal thermoclines. So depending on the season, right, we can see how our seasonal thermocline or that changes. And so you can see that in March, we've got all one temperature, right? It stays around 4.25. It's not getting any warmer. It's cold. It's cold at depth. It's cold on the surface. In May, we start to warm up, right? It's relatively warm, and then we get back to that 4.25 pretty quick. And then in June and August, we see that we've got a smaller slope, right? So from, let's say 70 to 20 meters, it's gradually getting warmer until about 20 where it shoots straight up. So notice that our seasonal thermocline is developing. It's getting smaller and smaller. So where it shoots straight up is our seasonal thermocline, because that's what's changing, right? And from May to June to August, it's continuously getting shallower and shallower. Does that make sense? Okay, awesome. All right, so now we've talked about the Coriolis effect. We've talked about surface currents. Now we've talked about thermohaline circulation. So let's talk about, let's also talk about salinity. So Coriolis effect is surface currents. I know I keep saying that, but it's also for me to keep track of what I've been talking about. So Coriolis effect is for our surface currents. We've talked about our different isotherms, or how temperature affects currents and makes layers effectively in the water of different temperatures. And our last sort of thing to pull this all together is salinity. Salinity is defined as the total amount of dissolved solids in seawater. So we think of salinity, saline, salt. It's not just salt. It's all of these dissolved ions that is in the ocean water together to form salinity. So we talk about salinity in parts per thousand. So this is the parts per thousand symbol, this little 0 over 2 zeros. You guys are probably really familiar with percent, right? This is just per thousand. So if we break down percent, it's per, which is by or for, and then cent, which is the Latin prefix for 100. So 1 cent, right? 1 out of 100. 100 cents makes $1. We can think about centimeters, which is 100 centimeters in 1 meter. There's a ton of things. Whenever you see cent, you automatically want to be thinking about 100. So per cent, and then this is parts per thousand. And so it is talked about or represented in parts per thousand, and it's when all the carbonate has been converted to oxide. So basically what that means is all organic matter, all fish bones, fish flesh, fish whatever, all the plankton, all the whales, everything has been completely oxidized. When that happens, that's when we're talking about salinity. There is no organic matter anymore, okay? It's all dissolved ions. So regardless of the range of salinity in the ocean, the ratio of the major dissolved constituents remains unchanged. So we can think about this, that might be like, wait, that doesn't totally make sense. But if you think about it as far as when you you're constantly having this balance of water being evaporated out of the ocean and also water being put into the ocean, right? And so that balance means that this ratio of the major dissolved constituents or the dissolved solids always remains unchanged. It's not like from day to day, the ocean gets noticeably salty or less salty, right? So the ratio always remains unchanged. But what is really important to note is that this is in like the entire ocean. It absolutely changes from specific locations to specific locations, which we're going to talk about next. But as far as across the oceans, the ratio doesn't change. And we will, that's going to make sense, I hope, in the next slide. So because chloride is the most common dissolved ion in seawater, that's how we figure out salinity. We set up the equation to say that salinity in parts per thousand equals 1.80655, which is a constant, right? This is that ratio, which never changes. That's why it's unitless, because it's a ratio, and we always use it, times the chlorinity. That always trips me up, which is also parts per thousand. So again, we've got salinity, parts per thousand, times this ratio that always remains unchanged, 1.80655, times the chlorinity, which is also parts per thousand. So what that means is if you've got the chlorinity, you can find the salinity. And if you've got the salinity, you can find the chlorinity. Okay, so let's talk about that ratio and how it never changes across ocean basins, but it might change in different locales. So in extreme northern and southern oceans, right, so we can think Antarctica and the Arctic, seawater temperatures are very, very cold, and sea ice begins to form. So as this sea ice forms, it basically freezes the water, but expels all of the salt from the ice. So what's happening is as, icebergs or ice caps are forming, the water around that area is getting saltier. It's getting more saline, right? Because fresh water is being captured into these icebergs, into these ice caps. And the dissolved ions, the salinity, is remaining in the actual water. So this is an example of how the ratio might change in specific locales, but again, it doesn't change over the whole ocean. And so what happens is as salinity begins to increase in the water and as temperatures begin to decrease, right, because it's cold, as you take salt out of water, maybe you guys know this from cooking, right? But if you add salt to water, it boils faster. Right? If you take salt out, it's going to take a longer time. So as salinity increases, as you're adding more dissolved ions and the temperature is decreasing, that surface water becomes way more dense and it begins to sink. So as it sinks, surface water is pulled in from elsewhere. It begins to cool, freeze, and sink. So instead of talking about it, how about we draw it out? So let's imagine, I'm going to draw a really good iceberg, just like that. It's really good. Okay, so my icebergs are forming. I'm gonna color it in, so good. My icebergs are forming and my water here, it's choppy seas. My water is getting more dense, more saline, very much colder, and so it's going to get more dense, and so that water begins to sink. And so if this water is sinking, you know, water is a fluid, right? It moves into space that it moves into an unoccupied space. So as this water sinks, it's got to be replaced by something else, and what it's replaced by is surface water elsewhere. So I thought that would be a darker blue and you could tell the difference. I'm going to do red instead. So this surface water is warmer, it has less salinity, and it's flowing in to take the space of this denser water that is sinking. And so it's going to create, yellow is going to be my little like in-between phase. It's going to create this circle, right? I've got dense water sinking. It gets super, super cold and spreads out. As it spreads out, it's going to mix with warmer water that's away from the iceberg, less saline water. It's going to start to rise, and then surface water is going to come in and fill this void space, basically. And so this causes the thermohaline circulation. So if you want to think about this in like a really rapid time, let's think about when a boat sinks. So when a boat sinks, you don't want to be anywhere near the boat, right? Because it's going to pull you down with you, which is really morbid. And sorry, that was not a good example, but that's all I got. So that's the same sort of thing that's happening. This is pulling water down with it, and it's sucking in this surface water from elsewhere to sort of start this whole thing over again. So the surface water comes in, it gets colder, it freezes into ice caps. That fresh water is frozen. The dissolved ions makes the surrounding water a lot denser. It sinks and it keeps going. And so that is what's causing thermohaline circulation, which is one of the drivers for deep ocean currents. So anything under, or sorry, yeah, deeper than 1 kilometer. So this is, let's put some text. This is deep ocean current. Nope, that's not how you spell ocean. Let's talk about surface currents. So my, oh, I didn't, well, whatever. So this is my surface currents over here. So surface currents can also have water sinking and rising. So I'm going to put a little line here as the difference. And so, but this involves wind instead of density. So I'm going to keep that yellow and have a little, this is my shore. Actually, I want an arrow. This is my shoreline, and we can have 2 different things happening, right? We can either have wind blowing towards the shore, or we can have wind blowing away from the shore. So we'll do towards the shore first. So what happens is when the wind is blowing towards a coastline, an area of surface convergence forms. And that word should be familiar to you all, right? Like convergence, like convergent boundaries. Same sort of thought process. We've got 2 things that are acting on one another. We've got 2 forces that are converging. And so what happens, just like in a tectonic setting, is something starts to sink. And so downwelling occurs and ocean water will start to sink. So in these convergence zones, convergent zones, we've got downwelling, which just means, again, ocean water sinking. Oppositely, we can have, that's not what I want. Oppositely, we can have, is oppositely a word? Maybe. We'll say it is. We can have areas of divergence. So you also might be like, hey, divergent, that sounds familiar. It's also a tectonic setting, right? So in these areas of divergence, we can get deeper ocean water rising or upwelling. So same sort of deal as a divergent boundary where you've got magma upwelling and creating new crust. Here we've got deeper ocean waters rising up, right? Warming, this cold ocean water rising up, warming, becoming surface water, right? So again, we've got 2 different types of forms with wind-driven surface currents. We've got convergence, which is when the wind is blowing towards the coastline and it's creating downwelling. And we've got divergence, which is when the wind blows away from the coastline and causes upwelling. All right. So with all that, let's do some math. So we're going to go to currents. And we're going to head to questions 10 and 16. So we're going to do a unit conversion, and then we're going to do a salinity equation. Really quick before actually, no, I'll get to that later. Sorry. All right, so question 10. Give the concentration of seawater with a salinity of 3.9% or parts per 100, right, and parts per 1,000. So whenever you have a conversion, any type of unit conversion to do, I always like to set up a Venn diagram. I'm going to make this huge because the text in Zoom is ridiculous. That might be too huge, but we're going for it. So fence diagrams help me in two ways. One, they make sure that I'm keeping track of my units. And two, they make sure that I am dividing what I need to divide and multiplying what I need to multiply. So whenever you have a fence diagram, you always want to just start with what you know. And what I know is that I have 3.39 parts per 100. So I'm going to go ahead and write that down, 3.39 parts per 100, which is just percent. And I don't want this to be green. I want this to be red. Okay, so there's my starter, 3.39%. And I know I want to go to per 1,000, right? So in math and anything, when I want to get rid of a unit, I need to cancel it out, right? And so what that means is I know, without even knowing the numbers that I need to put down, I know that at least on the bottom here, I need to have a percent sign. And up here, I'm going to do PPT as parts per 1,000. This is what I know I need to end up with. Percent gone, PPT there. So I'm going to go ahead again, before I put any numbers, I'm going to cross out. I'm going to cross it out the other way so you can actually see it. Cross out my percent. Because already I know I'm set up. My percent's gone. I'm left with parts per 1,000, which is what I need. Okay, and now I just got to fill in the numbers. So I'm going to move this over here so I got some room. Okay, so in this case, it's super easy. I know I have parts per 100. I know I need parts per 1,000. So that's exactly what I put into the fence diagram. On top, it's parts per 1,000. So I put 1,000. On the bottom, it's parts per 100. So I put 100. So I got to multiply by 1,000 and divide by 100. I could also just multiply by 10. Why can I do that? Because of math and crossing out zeros, right? But I want to make sure that I'm not making any mistakes. So I'm going to do it the long way, which is 3.39 times 1,000 divided by 100. And so what is that? Can somebody tell me? Anybody just be brave.
3,390.
Yeah, exactly. And then what is it divided by 100? Oh, I heard somebody say something, but I couldn't quite hear it.
Shouldn't it just be 33.9?
Yeah, perfect. 33.9 what? Percent? Definitely not. Yeah, exactly. Parts per 1,000. Perfect. Good. Awesome. I'm going to show you guys one more way to do this, just in case, because people learn different ways, and I think it's important to learn in different ways. So, anyways, so you got 3.39%, right? And so I am in parts per 100, and I know I got to get to parts per 1,000. So here's what I'm going to do. I'm going to use sig figs. Do you guys remember? Oh, I just deleted it. That was very good. Do you guys remember significant figures, right? All that means is moving decimal points, right? So I'm going to move these decimal points. So I'm at parts per 100. I want to get to parts per 1,000. So what I do in that case is I can do two things. I can either do the long way like I did here, and I can multiply by 1,000. So that means moving my decimal 3 times. So if I do that, or, and then moving it back 2 over, which would leave me at 33.9. Or what I can do, which I think is the simplest way, is remember to cancel out my zeros like this and just move my decimal point over once because it's 10. And that's going to leave me with 33.9. So depending on what you feel comfortable doing, you can either do the fence diagram or you can mess with the sig figs with the decimal places. But either way, as long as you are keeping track of your units, keeping track of the decimal places, you should be good. You should be good to go. Just use whichever way makes more sense to you, whether it is moving decimal places with sig figs or doing fence diagrams. For me, fence diagrams are 100% the way that I go because it allows me to keep track of what I'm doing. It allows me to keep track of units, and I can very clearly see how I got from point A to the end, right? With sig figs, if I make a mistake, sometimes it's really hard for me to figure out where I went wrong as far as moving the decimal place. So if it was me, I do the fence diagram, but all that's important is that you understand what the question is asking you, and making sure that you can replicate it, basically. Okay, so that is question 10. Let's do 16. So I'm gonna delete all this. Can I just clear this maybe? Yeah, okay. So for question 16, we're talking about salinity. So we remember that this is our equation, salinity. So this is in per mil. Remember that we usually talk about salinity in parts per thousand, right? So we notice that this is per mil, and that's different than what we're used to. So that's going to be a point of concern. So what we want to make sure is that our chlorinity that our salinity is also in per mil. So this question says, what is the salinity of seawater with a chlorinity of 19.65 per mil? So that's our concerning point. We've got chlorinity and 19.65 per mil. We know that we usually talk about salinity in parts per thousand. So we might have to do a unit change here. But before we panic, I want to keep reading. And we notice that it says, salinity per mil, thank God, equals 1.80655 times chlorinity per mil. So turns out we don't have to do any unit changes, right? Because we've got per mil equals per mil. If we had read salinity parts per thousand equals 1.80655 times chlorinity per mil, then we would have to do a unit change, right? Because we've got to make sure that our units always match. Because this is a ratio, it doesn't have any units, so it's all up to chlorinity to match salinity. And in this case, it does, so we're good to go. All we have to do is plug and chug. So salinity equals, I just blocked out the equation with Zoom, equals 1.80655 times 19.65 per mil. So again, no unit changes. And what does that equal?
35.5 if you round.
Yes, somebody is saying something. I'm going to trust that you're totally right. What did you get, like 30 something probably?
35.5 if you round.
There you go. Yeah, awesome. Sorry if that was you in the beginning, Charles. I think my headphones are just like acting up. But yeah, exactly. So we don't have to do, again, any unit changes. It's 35.5, I think you said, per mil. We make sure that salinity matches chlorinity, and that's it. We're good to go. We can move on with our lives. Last thing I want to show you before I turn you loose is just to make sure that you, for this lab demonstration, watch this video. And also, here's the Word document that you'll fill out. So you can either click on this here. If that doesn't work, I also have this link, which is a Google Sheet. And if that doesn't work, I also put a PDF on the As You Learn page. So you've got 3 different choices. If you decide to use the Google Sheets, please, 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 please download the sheet before you work on it or make a copy or something, but don't just open it and then start writing random stuff in here because as Google Sheets does, it saves. So before you do anything, file, download, and then you can mess with it, okay? If you don't want to use Google Sheet, if you would rather use a PDF, there's a PDF on As You Learn, but watch this video first.